Today we are going to discuss multiple linear regression where it has more than one predictor variable involved in the model. Multiple linear regression, when it comes to that, we always have one response variable or one y variable, but we have more than one predictors or x variables, right? So last time we discussed how to incorporate the matrix approach um, to evaluate simple linear regression. So it's going to be the same here. There's no other way of doing this rather than going for the matrix approach. There could be ways, but this is the easiest and this is the most recommended. And it's just a matter of changing the data matrix or the design matrix. And there's a couple of things that you have to consider. So it's going to be exactly the same sort of computations that you did last week. So in multiple linear regression, we say the model, we discuss the model with P number of predictors. Remember, this P is not the number of parameters. It's the number of predictors, the number of X variables, right? Because if we have X, P number of X variables, we have P plus one number of parameters, including this intercept, right? So a regression model with P predictors and normal error terms is defined as this one. Okay, so if someone asks to define the regression model with the multiple linear regression model, you have to copy and paste this slide, right? What does it mean? You have to specify the number of predictors that you have. It doesn't matter if you use another notation for this, right? But you have to say we have P X variables, P predictors, okay, number of X variables. Likewise, write this model and you have to write all these assumptions just like SLR. Otherwise it's wrong, it's incomplete, right? Because these, to accept this as a regression model, it has to meet all the assumptions. So where these are the parameters, it's quite obvious, but still you have to write it, right? Beta naught up to beta P are the parameters. xi1 up to xip are the known constants or the predictors, right? Why do we call it constants? Because we have our data set in hand, right? But they are the predictor variables. Epsilon I, they are identical and independently distributed with mean 0 and constant variance where I goes from 1 to n is the sample size. So you have to write all these and you have to say P is the number of predictors if you are asked to define a regression model with P predictors, right? The regression model is called first order model with P predictors. Why? It doesn't have any interaction terms. X1, X2, XP, likewise, we don't have X1, X2s, right? There could be a complex regression model as well, likewise. It can have square terms, cubic terms. So it depends. That is coming under model improving. So basically, from scratch, if we are talking about this is the simplest model that we can come up with. We call it the first order model with P predictors. First order, because it's to the first power of all these. In this model, the effects of predictor variable on the response variable y are additive. It's not multiplicative. Why? We don't have multiplications of x's here, right? It's additive. It is an additive model. Anyway, to define a regression model with pre-predictors, you have to write from here to here. That's it. Okay. Meaning of regression coefficients. Beta naught represents the mean response expected value of y and all the predictors equal to 0. Intercept. This is intercept is the name given to this. You already know this. It's the same thing for simple linear regression as well. There we talk about at the predictor equal to 0. Here we define it as all the predictors, just because we have multiple predictors. Parameter beta j. So j goes from 1 to p because we have p number of x's. So beta 1, beta 2, beta 3 up to beta p. Those are going to be the coefficients of each and every x variable that we have in our model. So parameter beta j indicates the change in mean response, expected value of y, per unit increase of xj when other predictors are held constant. When we talk about simple linear regression, how did we interpret our beta values, right? A unit increase in x will result y to increase or decrease, whatever it is, depending on the sign, beta 1 units, right? That's how we interpret it. Here we are going to add a small phrase, when other predictors are held constant. We are talking about one at a time. If we are going to interpret beta 1, we have to say unit increase in x1 will result beta 1 increase in y when all the other predictors are held constant. Right? If we are talking about beta 2, we have to say a unit increase in x2 will give an increase to y in beta 2 unit. It could be increase or decrease. It depends on this sign. Okay, unit y is increased in beta 2 units when all the other predictors are held constant. So that is the most important part here. That is the addition that we have in our interpretations of coefficients when it comes to multiple linear regression from the simple linear regression. So this is very important. Change in mean response. Okay, it's the mean response, not in y actually. Mean of y changes. Okay, regression model with two predictors. So when p is equal to 2, right, you have this one. y1 is yi is equal to beta naught plus beta 1 x1 plus beta 2 x2 plus the error. Error is independent and identically distributed with 0 mean and constant variance. Error terms. Same thing when p is equal to 2. Beta naught is the mean response when x1 is equal to 0 and x2 is equal to 0. That is correct, right? When this is 0, when this is 0, this is equal to this. Mean response because mean of epsilon I is 0. So mean of this is 0, this becomes 0, this is 0, this is 0. Then expected value of y or the mean of y is equal to beta naught. That is how you interpret this. Parameter beta 1 indicates the change in the mean response per unit increase of x1 when x2 is held constant. So when you have only two predictors, you don't have to say when all the other predictors are constant. You just have one other predictor, right? So you can say when x2 is held constant. If you have x1, x2, x3, you can say the parameter beta 1 indicates the change in the mean response per unit increase of x1 when x2 and x3 are held constant. Or there you can say this happens when all the other predictors are held constant. But here it's obvious you don't have to use the word all the other. You just have one other. So that is how you use the language. Similarly, parameter beta 2 indicates the change in the mean response per unit increase of x2, right? When this is increased by 1 unit, this one increase or decrease by beta 2 units. You have to exactly say whether it is an increase or decrease. Here we are giving it in general, right? But you have to say when x1 is held constant. when you're talking about this, you have to let this one constant. When you're talking about this, you have to let this one constant. Interpret it. Right. Interaction effects. We are not going into deep in this, but it's important to know that there could be things like this. We within our scope, we are discussing only the first order models, the additive models, but here there is something like this. About general linear model, general, it's a linear model, assumes that the effect of one predictor variable on the response does not depend on the levels of the other predictor variable. That is what you mean by the additive model. If it does, you say there is an interaction effect, right? However, when the effect of one predictor variable on the response, effect on some x on y, depends on the levels of the other predictor variable. Just assume the other predictor variable is a categorical variable. We'll discuss how to handle categorical variables in the next lecture, right? Let's assume that x1 is age, x2 is gender, something like that. So if the dependency, if the effect of this to this is depending on the levels of these, that means for females there's one behavior, for males there's another behavior, something like that. That means there is an interaction effect, right? Interaction effect. However, when the effect of one predictor variable on the response depends on the levels of the other predictor variable. So if the other predictor variable is gender, what are the levels? Male and female, right? Then it is called, there is an interaction effect. It's just a word, but there's a couple of things that you have to know about this. So in general linear model with interaction effect for two predictors is this one, right? So this is not more an additive model. You have some multiplying terms as well, right? So if x1 and x2 has some interaction effect, means what? You have to incorporate another beta variable and beta coefficient and have this interaction effect. So in complex analysis, we can really see whether these are significant, these terms are going to be there in the model or not. Because what we try is usually to keep the model as simple as possible so that it's very easy to interpret and it's easy to use. But it's not the case all the time. We have to go with the correct, a good model, a well-fitted model. So we have to balance all these. So in a case where we found out that there could be an interaction effect, we are not sure, but let's assume that there could be some interaction effect that is coming from experience. We can incorporate a term like this to our usual model, and we can run an ANOVA and all that and see whether this is really going to stay here or not. If not, we can just take this off. If yes, we have to keep it. Same assumptions holds. In the presence of interactions, do not interpret the main effects. So if this is a significant term, do not interpret these things, right? It's meaningless to interpret the main effects, the effect of this on this, the effect of this on this. We do not interpret that. That means if this is significant, we are not going to interpret beta 1 and beta 2. That is meaningless. We can interpret, that is meaningless. That's not going to be meaningful at all if this is significant. If this is not significant, we can take this out from the model, or else even if you like, we can keep it, doesn't matter. But to make it simple, we can take this off and interpret the main effects. That means beta 1 and beta 2. So that comment is on interpretation. Matrix approach to general linear regression model. Consider this one with pre-predictors and p+1 parameters, right? In matrix terms, this can be represented by this way. The same thing that we discussed last week in simple linear regression. It's just a matter of constructing this one. Others are all the same. Epsilon is a vector of normal random variables with mean 0 and variance covariance matrix this, because this has in different terms, right? So these diagonal elements will give you the variance, and it should be sigma squared everywhere. Theoretically, it should be sigma squared everywhere because we assume the regression model to have constant variance. Right. So this is the matrix notation. You can write it in either way, this way or this way. But make sure you write the assumption, the proper assumption, in whichever the notation that you represent this when you're asked to write the model for the simple linear regression approach. Right. So here y is a vector of responses. It's the same thing that we discussed last week. This is the data matrix or the design matrix. So we have a couple of ones here in order to do further computations, because we have to incorporate beta naught as well, not only beta 1 up to beta p. So earlier we had only two columns, right? The column of ones and the values of the only predictor variable that we had. Here we have p number of predictor variables, so we should have p+1 columns here. P columns for all the predictors and another additional column to have one. So in multiple linear regression, this is the difference when constructing the design or the data matrix. Here actually we have this is the beta matrix, beta vector you can say. So how many betas that we have? Beta naught up to beta p. We have p+1 betas. So after doing the matrix computations, we can obtain the beta hat matrix, that is beta hat vector, that is the estimated value of all the betas, all the regression coefficients, by using the same formula, x transpose x inverse x transpose y, if you can remember last week, right? So this is the only difference we have. And we have a vector of error terms. If you have any questions, please interrupt me and ask. Otherwise, I'm doing this. So estimation of regression coefficients. Similar to the simple linear regression model, regression coefficients can be estimated by minimizing the error sum of scores. You can either go with maximum likelihood, but last time we discussed how to minimize the errors. So what is the error here actually? By the response, you have to subtract all these. If you want to isolate error, what have you got to do? By this one, you have to subtract all these, right? And you are considering the squared summation of errors. You take the squared sum, and that is Q. So our intention is to minimize the error. We cannot let the error term become 0, but the expected value of error, the average error should be 0. Error 0 means what? We have overfitted, right? We have gone through each and every data point. We are not doing that, right? We are just generally giving a line, because data are noisy, right? Data are noisy. It's not, it depends on the sample. So we cannot say the errors should be 0. No, we are trying to let the error very close to 0. Error 0 means we are overfitting the model. That is not advised. So here we are trying to minimize the error sum of squares. So this is how you get the error sum of squares. And when you do the math by using all the matrix derivatives, you can try that. You are getting this one, the least squares normal equation, this one. So when you want to isolate beta hat, right, you are taking the inverse from the left side. So it is x transpose x inverse x transpose y. Same thing that we discussed last time. Beta hat is given by x transpose x whole thing inverse times x transpose y. Right. So the ANOVA results, I think we discussed last week. We derived all these. SST, it's the same thing, just as a simple linear regression. This is the formula, the matrix formula to compute sums of squares of total, right? And sums of squares of error. And this one minus this one will give you this one. So derivation of these things we did last time. SSTO, SSC, and SSR is going to be the same thing. When you are substituting values, only this thing changes. Because we have a new formation of a matrix to X. Others all remain the same. So it's important for you all to know the formation of this one. Two of these, if you know just two of these, it's enough, right? You can take the gap between these two and compute the other one. You don't have to substitute everything at each level, right? Just substitute something easy and then get the other one. So that is the ANOVA result. And this is the ANOVA table, the usual ANOVA table with a little bit of difference. So the source of variation, sums of squares, degrees of freedom, mean squares, and finally you can have F, another column for F ratio. Here the source of variation goes from regression, error, total, right? So SSR is this formula, this one, same thing, right? We derived these things last time. And error is this, total is this, degrees of freedom. So there's a difference here. In simple linear regression, we had just 1 degree of freedom all the time for when the source of variation is regression. Why? Because we just have only one predictor variable there. So as degrees of freedom, you can remember this. If you cannot take this by thinking, always put the number of predictors here. Number of X terms that you have as degrees of freedom. So in this model, you have P number of X's, X1 up to XP. So degrees of freedom is P. In either simple linear regression or multiple linear regression, we know the degrees of freedom of total is going to be n-1. So this one minus this one will give you this one. When you expand this, you are getting n minus p minus 1, right? So n minus 1 minus p is this. So you have to remember this one and this one only. How do you get the mean square? It's the same thing. SSR divided by the corresponding degrees of freedom. You're getting the mean squared regression. Here, SSC divided by the degrees of freedom, you are getting MSE, mean squared error. You do not divide this one by this one and put something here that is wrong. We discussed that in simple linear regression as well. That is incorrect to do. So don't write anything here. How do you get the F ratio? The column is not given here. Same way, this one divided by this one will give you the F ratio. And how do you compute the critical value and all that? This is the numerator degrees of freedom. This is the denominator degrees of freedom. So actually that is the benefit of constructing ANOVA because we have all the data here, all the details here. It's just a matter of writing steps thereafter. So you have to carefully compute these things to the given number of decimal places. I'll tell you that at the end of the lecture what was happening there. Because these are sums of squares, these cannot be negative anytime. It should be positive all the time. So you have to carefully deal with the decimal places as well. I'll tell you that. So here the hypothesis is going to be changed. Earlier we had beta 1 equal to 0 versus beta 1 not equal to 0 because we just had only one x variable. So to see whether the model is significant or not, we had to see whether beta 1 is going to be 0 or not. That's all what we had. Here, our hypothesis is all beta i's are equal to 0 versus at least one beta I is not equal to 0. You can reword it, not all beta k equal to 0, where k is going from 1 to p. You can exactly write this, right? Or else you can say at least one of these. At least one of these should not be equal to 0. Let's say beta 1 is equal to 0, beta 2 is equal to 0, beta 3 is not equal to 0, 4 is not equal to 0, beta p is not equal. Let's say something like that. So beta 3 is the only thing equal to not equal to 0. Everything else is equal to 0. But still, we say the model is significant because you have that coefficient there in the model, final model, right? So this is the way. Don't say it's not. H1 is not that beta 1, beta 2, everything not equal to 0. No, that is not the way. Okay, at least one of these should not be equal to 0 to let H1 correct. So you can clearly write it. If you don't want to think and write, just by heart this and write. This is correct. Okay, or you can say at least one beta I is not equal to 0 where I goes from 1 to p, beta k or whatever it is. Right, so just get the idea. H0 is everything is equal to 0. H1 is at least one of these, at least one. Even everything would not be equal to 0. We don't mind that. At least one beta is not equal to 0 is going to be this one. So you have to be careful in forming the hypothesis in multiple linear regression. Is that clear? This is very important. Is this clear?
Yes, madam.
Okay, thank you. Right. Note. Above alternative hypothesis implies that at least one, same thing I just told, beta k not equal to 0. You can write it like this as well. So what is the test statistic? F star or F or whatever it is, MSR or MSC. That is the F ratio that we computed here. You can have one more column. So when you ask to write the ANOVA table, just have the F ratio column as well to make it complete, because you are given marks for that as well. This is not complete. You have to have F ratio. So MSR divided by MSE. So that is the basic test statistic. Here we do the F test, right, to check this hypothesis. And it is distributed as F distribution. This is the numerator degrees of freedom. This is the denominator degrees of freedom. How did you find that? It's there in the ANOVA table. Top one is the numerator one, bottom one is the denominator one. Very easy to capture from ANOVA table. Carefully construct this. The rest of the part would be done automatically. Decision rule is reject the null hypothesis if the calculated value is greater than or equal to the critical value. You know, F distribution is a positively skewed distribution, and the right hand side is the rejection region, right? So this is the critical value that we are comparing the test statistic value with. So when it comes to the rejection region, it falls to the rejection region if the calculated value is greater than the critical value. So that is how you form the decision rule. Same decision rule as SLR. You don't have to by heart this, you can just draw and get it. But anyway, in the paper, if you are asked to check the model significance, you have to write all these. It's not H1 statement, test statistic, decision rule, decision, and conclusion in plain language. Everything should be clearly specified, and the degrees of freedom is, the significance level is alpha. It's, this is a two-sided test. This is a two-sided test. But in F, we are getting it from a single side. That is why this is not alpha over 2. This is alpha. That is how we extract information out of F distribution. Hypothesis is two-sided. Right. Inferences about regression parameters. The variance covariance matrix of beta hat. So here, this is given by this formula. It's very easy. The parameter, the variance times this quantity, X transpose X inverse, right? So as long as this is a parameter, we don't know the value of this. So we are going to estimate it. How do you estimate the variance? We use the mean squared error. So instead of this, we can put this one, and this is the true variance covariance matrix. This is a matrix actually, because we have multiple values, and this is a matrix, right? It's not just a single value. It's not just a single variance value. We have p plus 1 beta. So we should have p plus 1 times p plus 1 variance covariance matrix. All the diagonal elements show you the variances. Of diagonal elements show you the covariances between each and every beta. So to estimate this, this is the notation. This is the true value. This is the estimated value. Notation that we are discussing from the very beginning. So MSE times X transpose X inverse. This is how you estimate the variance covariance matrix. In simple linear regression, we didn't have a matrix. We just had a value, the variance. Here we have covariance terms as well, because we have more than one beta. Interval estimation of beta k. For the normal error regression model, p number of predictors, we have this one, the same t-test, the t statistic, not the t-test, t statistic that we are using. So we take one at a time. So when k is equal to 0, we are doing the interval estimation for beta 0, the intercept. So this is the estimated value. This is the true value divided by the square root of, I cannot say square root of this actually. This is a matrix. You have to take the square root of the corresponding beta value, right? So if it is 0, you have to take beta 0 here. I'll explain that to you. So the 1 minus alpha 100% confidence interval for beta k is given by this. This is an interval, right? So when you have p number of predictors, you can have p plus 1 number of intervals. For beta naught, you can have one interval. For beta 1, you can have another interval. Likewise, up to beta p, from beta naught to beta p, you can have p plus 1 number of intervals. So you should know how to extract information out of this. Yeah, so explain that. It's easy. Okay, so let's assume our variance covariance matrix of beta is something like this. So I'm just writing values. Okay, so by looking at this, what can you say? We have beta naught, beta 1, and beta 2. Right, that means we have x1 and x2 in the model, right? So this is going in order. This column is for beta naught, this column is for beta 1, this column is for beta 2. Here this row is for beta naught, beta 1, and beta 2, right? So the variance of beta naught is this one, right? So if you are asked to write a confidence interval for beta naught, right, how do you write? The value of beta naught, value plus or minus the t statistic, right, times this one. This one is here. You have to get the square root because this is the variance. You have to take this square root of variance to get the standard deviation, right? If you are asked to write the confidence interval for beta 2, you know how to estimate this, so you can take whatever the value, estimated value for beta 2 plus or minus that t statistic times what is the value that you have to get. So corresponding to beta 2, this value, right? If it is beta 1, beta 1 hat plus or minus that t value times this one, beta 1, beta 1. So that is how you read this variance covariance matrix in order to compute the confidence intervals. So here you always have to get the standard deviation. Please remember that. If this is the matrix of standard deviations, you don't have to get the square root, but this is, we are talking about the variance covariance matrix. So what does it mean by this one? What is the meaning of this one? It's the covariance between beta 1 and beta naught. I don't know whether you notice this is the same as this. Why? It's the covariance again between beta naught and beta 1. Right here, it's the covariance between beta naught and beta 1. So these two has to be the same, right? If you take another one, this one and this one, they are the same. This means covariance between beta 2 and beta naught. Beta 2 and beta naught. So it should be the same with this covariance between beta 2 and beta naught. Here beta 1, beta 2, beta 2, beta 1. So all these values should be the same. I hope you noticed that. So these are the covariance terms, right? The variance terms are given by the diagonal elements. So when it comes to standard deviation, you have to get the square root. And remember, as these are variance terms, they can never be negative. You anyway cannot get the square root of a negative value. Variance is always positive. But when it comes to covariances, it could be negative. That is why we usually do not write the square root of this matrix, because sometimes you can get negative values, negative covariances. So they are not defined. We are not talking about complex numbers here. So from this, remember, if you are given this, or if you have constructed this by using MSE times X transpose X inverse, you are getting the variance covariance matrix. And if you are asked to construct this, remember to get the square root, right? Is this clear? Is this clear?
Yes, madam, it's clear.
Okay, thank you. Right. So just because we had notations here, you might be wondering what's going on. But yeah, so you should be able to work this out with a counting example. That's why I showed you. So you can have any number of betas. I just showed an example for beta 0, beta 1, and beta 2 when you have 2 experiments. Right. This is the t value. T minus 1. And remember the significance level, this is alpha over 2 because it's symmetric and we are getting from the 2 tails. So you can read this from the statistical table, right? You know the value of n, the sample size, you know the value of number of predictors, p and t. So this is going to be the degrees of freedom, right? If you have constructed the ANOVA table, that is simply this one. Same thing, same degrees of freedom. You don't even have to remember this formula. T, the degrees of freedom, you have to put the error degrees of freedom here. That's it. And alpha over 2. Same way. This is the square root of the corresponding beta element of this. Kth beta element. Okay. Test for beta k. So this is just one test. So when k is equal to some value, h0 is this one, h1 is this one, right? The test statistic is this. So this is the t-test we are talking about. If we want to individually check each and every beta is significant, we can go with the t-test. In software, actually, they give ANOVA table with a couple of F ratios. I think it's the T ratios, a couple of things to decide which betas are significant at that ANOVA table level. But here we are writing the general ANOVA table. All the X's are included in this one. We don't have separate source of variation for each and every X here. This is what we have to compute. So in software, they give the breakdown of this. We are not going to compute that. And then and there you can find what are the significant variables. So here we are doing the F test basically to check this hypothesis, right? Assume that you rejected H0, that means at least one beta k is significant. right? At least one variable is significant, but you don't know how many variables are significant. What you know is at least one is significant, right? By this test, if this is rejected, you don't know which variable is significant or which variables are significant. You don't know. But what you know is this model is somehow significant. It could be used. If you want to individually check which variables are going to be significant, you can do this test one at a time, right? If you want to check whether the intercept term is significant, so this beta naught is equal to 0 versus beta naught is not equal to 0, and by the variance covariance matrix you can read this term, right? You know the estimated value of beta naught hat, right? Same thing, you perform the t-test and this is the decision rule. It's the same one sample t-test that we have learned before in other courses, mathematical statistical courses. We take the absolute value and check whether it is greater than or equal to the critical value, right? Actually, you can, this could either be positive or negative, right? That is why we take the absolute value, so it goes to the right hand side end of the t test. It is not clear, let me explain that. This is out of scope, but good to know. If this is the t distribution, right? It's symmetric around 0. This is alpha over 2, this is alpha over 2. That's how you get the alpha totally, right? So when we compute the test statistic value, right? There are two possibilities, right? This could be either negative or positive. Why? It can either go somewhere here or somewhere here if the hypothesis is rejected. There are two rejection regions, right? If t is less than 0, it has a possibility to go here. If t is greater than 0, it has a possibility to go here, or these ones, right? So actually the decision rule is reject H naught if T star is greater than, let's say, T critical 1, T critical 2, right? Just because of the symmetry, T critical 1 is equal to negative T critical 2. Just have this notation for the moment. If this is greater than TC1, or actually this is the decision rule. This is very lengthy and no point of checking two things. That is why we reconstruct this decision rule as reject H naught if absolute value of T star. So when you get the absolute value of this side can be omitted because less than 0 values are not there, right? Alpha over 2 is there when you take, because of the symmetry we can do this. If this is not symmetric around 0, we cannot do this. We cannot reconstruct this decision rule like this. It has to be symmetric, and at the same time it has to be symmetric around 0. Otherwise taking the absolute value will never help you. So either T star is positive or negative, you can reject if the absolute value falls here in this region. That means if the absolute value is greater than TC1, the critical value. Okay, so that is the decision rule discussed here. So what I want to emphasize here is, actually, if you have the idea about the distributions, you really don't have to by heart any decision rule. Not any, but at least a couple of things you can construct and get. This is the idea, because there are so many hypotheses that we are checking, and I know it is hard to remember all those. If we can construct something like this, that is easy. Okay. So that is why they have given the decision rule like this. reject it because we are checking one at a time. They say this quantity follows a t distribution, so it's going to be a t-test. Reject it's not if this computed value is greater than or equal to this value. So you can do individually, you can perform this test individually for all the beta case that you have, one at a time. Here we did everything at the first time, right? This is the way. If we accept it's not here, what's the information that we are getting out of this? If it's not is correct, that means the entire model is not significant. At least even one predictor variable is not significant. The model is useless, right? If we accept it's not here. So if we can accept it's not here, we don't have to individually check, right? We know everything is 0. If assume that we rejected it's not here, right? Assume we rejected it's not here. All what we know is at least one of these are significant, right? So how to find that? Which one is significant? Which two are significant? Is everything significant? Is only a couple of things significant? How do we know that? We have to individually check it. That is why the t-test is discussed here, right? You might be wondering why f test is given, t test is given. No, two different hypotheses. First, we do the ANOVA f test. If H naught is accepted there, we don't have to do this. Even if we did this, we are going to accept H naught for all the betas, because we initially said that all the betas are equal to 0. In case if we reject H naught, we should be able to find which betas are significant, which predictors are significant. So for that, we have to individually perform tests for each and every beta and drop off whatever the insignificant things and include only the significant parts in the model. This will help you to simplify the model. Otherwise, if you reject H naught here, you can have all those terms in the model and use it. It's going to be very complex. There could be insignificant terms as well in the model. It's not going to add high value because they are insignificant, but still you have to incorporate a very complex formula if you cannot omit insignificant terms out of this. So that is why if we find out that this happens, the next step is checking what betas are significant, and we are going to reformulate the model. That is the use of this test. Even with the confidence interval, you know that, right? If you construct the confidence interval for all the betas, right? And if a particular confidence interval includes 0 in that, that means that particular beta is not significant. Let me explain that clearly. Let's assume we have beta naught, beta 1 and beta 2 for the moment, right? Say we have a confidence interval 2, 3. Something like this. I just wrote the values. Okay. So this is the confidence interval for beta naught, right? So beta naught, we are, let's say 95%. We are 95% confidence that beta naught falls between these two values, right? Is 0 including here? Is 0 between these? No, 0 is somewhere here, right? 0, 2, 3. So 0 is not included. That means we are 95% confident that 0 cannot, beta naught can never be 0, right? That means beta naught is significant. It doesn't have a possibility to become 0, right? This one, 0 is included here, right? Between -1 and +1, 0 is included here. So there is a chance that beta 1 can be 0. So therefore, beta 1 is insignificant. We can drop this particular term from the model. By looking at confidence intervals, you don't have to perform even the t-tests. There are a couple of ways, right? Here, beta 2 can take values between these two, lower limit and the upper limit. Again, 0 is not included here. 0 is somewhere else, right? So which means beta 2 should be in the model. So you can do t-test and check these. This one, and you will find that you reject H0 from the t-test, right? So this is another method. If you have already constructed the confidence interval, you don't have to do the t-test. It's the same result that you're getting. You can do and see, right? From here, of course, you can decide that this is significant, right? So given the situation, here the correct hypothesis should be this one. Here, again, we are checking beta 1 equal to 0 versus H1, beta 1 not equal to 0. Here, we found out that 0 is including in here. So even if we do the t-test, we accept H0. So we can just get rid of this term. Here, beta 2 is equal to 0 versus beta 2 is not equal to 0. Given that 0 term is not included here, even though you do the t-test, you are rejecting H0. Is this clear? There are two methods, doing the t-test or constructing the confidence interval. Both ways you can decide, same thing. Is this clear?
Yes, madam.
Okay, thank you. Right. So in the paper, I could ask that. Do a t-test and draw your conclusion. Construct a confidence interval. What can you say about this? So things like that I could ask. So you should be able to explain, right? These are easy things, very obvious things. So carefully take this into head. Okay. Coefficient of determination. So this is basically the R square that we are talking about. We usually determine the goodness of fit by using the R square, right? In simple linear regression, this is the formula that we use to compute R squared. Out of the total variance, how much of a variance is explained by the regression model? That is the idea, right? That is why you are getting the ratio between SSR and SSTO out of total, the sum of scores of regression, right? You can either keep it as a decimal or as multiply this by 100% and have it as a percentage, right? But when it comes to multiple linear regression, you cannot compute R squared like this. It is misleading, right? Note that adding more predictors to the regression can model only increase R squared and never reduce it. Because when we, in multiple linear regression, we have so many predictors. So we keep on adding predictors and our sums of squares of regression anyway increases. When we have a lot of predictors, every summation comes under this, right? So just because we have a lot of predictors in the model, we cannot say the model is good. We have to say the model is good only if it explains a considerable amount of variability that we expect. Out of the total variability, if the model can explain at least 80%, we can say it's a good fit. But in multiple linear regression, the SSR keeps on increasing, not because of the goodness of the fit, but because of the increasing of predictor variables. So that is not what we expect. So when it comes to multiple linear regression, we adjust our R squared by using this formula. We do some adjustment in order to avoid the increase of SSR due to the number of predictors that you have. So by adjusted R squared, or in other words, by this formula, you can exactly say whether this is a good model or not, right? So usually we take 80% as the figure, but when it comes to practical data set, it's really hard to find 80% well-fitted models. So it depends on the researcher, whether they're going to say it's a good model at the level of 80% or 50% or whatever it is. But generally, in simple linear regression, this is how you compute R squared. In multiple linear regression, we do not use this as a very good measure just because of this issue, right? When we have more predictors, this is anyway getting larger. So we cannot say whether the model is good or not. So we do some adjustment. The derivation is not included. So you have to compute this figure in multiple linear regression. R squared can be made larger by including a larger number of predictors. That is the issue. Hence, it is suggested to use adjusted coefficient of multiple determination. R squared adjusted is given by this. So you have to know this formula, where P star is the number of parameters in the model, right? P is the number of predictors, P star is the number of parameters, right? So if it is a very first order additive model, always P star is equal to P plus 1, but assume a case where you have interaction terms and all that. So it's not the case, right? It's P star is not always equal to P plus 1, but generally within our scope, it is equal to P plus 1. So you can either replace P plus 1 by this, but it's better to have this one because we don't know what our end model would be. What if we get rid of the insignificant terms? So there could be changes. So remember this formula like this. Here, it's not the number of predictors, but it is the number of parameters. P star is for number of parameters. Just remember it like that. So 1 minus this quantity. Here, the adjustment is done. So it's the same thing, right? 1 minus this one, 1 minus this one, but they have multiplied it by this particular quantity to do the adjustment for this issue, right? Same thing, it's easy to remember. Just remember only this part, that you have to multiply this quantity by this. You know how to compute this one. SSR, of course, you know the breakdown of SSR, right? SSTO minus SSC. So you can, if you know this one, you can get this, right? If you can remember this one, you can get this. So find some way of having these things in head. Right. All the graphical diagnostics tools discussed under simple linear regression can be applied for multiple linear regression too. Right? Lots of residuals versus predictor values, because it's the same assumption that we have. all the error terms should be constant, variance should be constant, mean error should be 0, likewise. So you can have the same diagnostic plots that you use to check the model validity. Plot of absolute or squared residuals versus predictive variables, plot of residuals versus weighted values, residuals versus time or the sequence to check whether the observations are independent, right? It should be fluctuating, it should be a wiggle shape. There should be a random order, right? When you plot this. Residuals versus omitted predictors, you can have either this, so this is something new, right? You can just check the patterns. Omitted predictors means the predictors that you do not include in the model. Box plot of residuals, normal probability plot of residuals, of course, they should be normally distributed. Okay, so this is a very small example. Don't misunderstand that this is a proper multiple linear regression question because we just have 6 things in the sample. Sample size is very small, it's 6. And this is just to make your computations easier because you are expected to do all these things manually, right? So let's try to do this example. I didn't calculate it manually, but I used a software to compute this. I'll show you that at the end. I'll give you time. So this is the last thing for today. In a small scale regression study, the following data were obtained. So this is our sample size is 6, and this is our first X variable. This is our second X variable, and this is our response variable, the Y variable. Assuming independent normal error term, you have to go for an additive model. That means y equal to beta naught plus beta 1 x1 plus beta 2 x2. That, okay. Obtain a regression model using matrix approach. Now you have to define the y vector, x matrix, right? Obtain the ANOVA table. Check whether the regression coefficients are significant at 5% level of significance. Further, obtain 95% confidence interval for beta 1 and beta 2. Yes, you have beta naught, beta 1 and beta 2, but you can take the variance covariance matrix and obtain confidence intervals for these two as well, right? You may use the following results, and just for your convenience, I gave this, but don't use this because I was in trouble when using this. I got negative values for ANOVA table sums of squares. That happened because these things are rounded off to the first or second decimal place. So that cannot be done. So use this one. Show that. Except 34.6, just have 34.5786. Likewise, just write this particular what is there in the comment. You can see where my cursor is, right? So that is a 3 by 3 matrix. The same thing with increased number of decimal places. Okay, so I have computed x transpose x inverse quantity to 4 decimal places. Actually, it has many decimal places, but when you are doing it manually, it's very troublesome to deal with a lot of decimal places. So just copy down this matrix for x transpose x inverse and do the rest of the computations to estimate betas first, and then obtain the ANOVA table, obtain the confidence interval for betas. So I'll give you time for that. We have like 1 hour's time. Don't get dropped from the class. I want you all to work out this, right? So if you have any question, just ask me. I'll give you time. First, give me values of beta naught, beta 1 and beta 2 by using this. Quickly start doing. Just use the this one. Disregard this one, okay? Disregard this one and use this one. just copy this matrix first, then I'll show you the data set, right? So that you can work out. It's better if you can take a screenshot, it's quick. I assume that you have copied X transpose X inverse matrix now, so I'll switch back to here so that you can design all these. Anyway, you have the lecture note with you, the comments are there, so even you can get this. First, give me the values of beta naught, beta 1, and beta 2 hat. Let's do that. Okay, I got one person's answer. Yes. Yes, correct. The one who responded me in the chat room, the beta hat matrix is correct. Very good. Now you can simply start constructing the ANOVA table by computing SSR, SSTU, and SSE, then the mean squares, degrees of freedom, and all that. Thank you for responding. Others also, please come up with answers. Okay, another person responded, the beta naught and beta 2 values are correct to the fourth decimal place. Beta 1 value, I think there's a small deviation from the second decimal place onward. So I'll give you the value because so that you can proceed. Because slight differences in these might do huge effects for the rest. So thank you for the approach. I'll give you the values of this. I hope others also can do this. This is very easy. Matrix manipulation. So the beta hat vector is, so when you are given X transpose X inverse that matrix, I expect you all to obtain the same answer. Right? Don't round it off because I'm giving you in a way that you can write all the decimal places. I won't expect you to write 10 to 15 decimal places. In the exam, I would give you a proper question in a way that everybody can approach the same way. Why I gave you the X transpose X inverse matrix is because I want you all to come up with the same answer. Sometimes actually that happened when it is rounded off to 2 decimal places, it gave me negative results for sums of squares. So that is not accepted. That happened due to rounded off errors. So here the answer is 34.1895. Just check your answers. So this is the value of beta naught. right? And beta 1 is this. The second person's response versus this is slight deviation in this one. Other one was correct, 0.2617. So this is the value of beta naught, this is the value of beta 1, and this is beta 2, right? Then I asked you to compute the sums of squares. So in the ANOVA table, just try to have them, just because the time is passing, I'll give you the answers, but please work it out, right? So SSR is, this is what I got, 2208.38. And SSE, just check your answers with these, 863.6149. SSTO is 3072, right? Okay, mean squared regression is 1104.193, where you have to divide this by 2, right? This divided by 2 will give you this. And MSE, just check the answers, it is 287.8716, right? So when you know this, you can get the F calculated value or the F star, right? That is 3.835 something. Okay. And get the critical value, F critical, you can read it from the table. That is 9.552 something. So this is basically F2 and N minus P minus 1, right? So this is 6 minus 2 minus 1. That is 3. Okay, the value is this. Then you have to obtain the variance covariance matrix. You can take a screenshot of this. Just check your answers. Please work this out. You are getting a question like this, so please work this out. Variance covariance matrix, it is quite big. So let me give that as well. I'll give the diagonal values only, right? Because off diagonals values are covariance terms, you are not going to use it. But if you're asked to compute the variance covariance matrix, you have to get everything, right? For the moment, I'll write only the off diagonal, the diagonal ones, because you are going to use only those. And remember, the value you are getting here should be the same value you are getting here. This value is going to be the same value as this. This value is going to be the same value as this, right? So this is the variance covariance matrix. Variance of beta naught, variance of beta 1, and variance of beta 2. Okay, so you can obtain the confidence intervals, right? So they have asked us to give the confidence interval for beta 1 and beta 2. So roughly, I'll give you the values that I got. This is negative 12.74. I'll just give it to 2 decimal places. This is 17.86, right? Beta 2, negative 6.35, 5.82, something like this you should be getting at the end, right? Just by looking at this, can you see 0 is included? That is what I want to teach you again. 0 is included here, right? Which means beta 1 is not significant. That means the corresponding predictor variable should not be in the model. X1 is not, it should not be in the model. Here also 0 is included. That means this model is not usable, right? It's not significant, it's not is accepted. So you don't have to even do individual t-test to check the model validity, right? By comparing these, can you see now what is F critical? 9.552. What is F calculated value? This one. It is somewhere here. It's not in the rejection region. Not in the rejection region, right? So we do not have enough evidence to reject H0. What is H0 here? Beta naught, beta 1, beta 2 equal to 0, right? We accept this. We accept H0. That means what? This model that we got, what is the model that we got? Y is equal to 34.1895 plus 2.5623x1 plus, sorry, minus 0.2617x2. This is the model that we got, right? So this model is not significant. That's what it says. Even by the F test, it is proved, right? If you do individual t-test, by using these, right? If you do individual t-test, the estimated value divided by the square root of that test, again you will be getting that beta 1 is not significant, beta 2 is not significant, right? When you do not have to do the t-test, just by constructing the confidence intervals also, you could see none of these are significant, right? So those are the conclusions that you can come into. Please know how to compute these things. Use all the theory. I gave these answers for you all to work out alone and check. Please check that, okay? Do it manually, because for the regression course, you are expected to get these things manually, right? Are there any questions regarding this? Any questions? Anything which is not clear? Is this clear? The way of computing this?
Yes, madam.
Okay, thank you. Clear. Okay, right. Right, please work this out, right? I gave you all the answers, right? I worked it out myself. I gave you all the answers. Please do it. You're going to be questioned on these. It's very easy, right? I'll tell you that these things are coming to the exam, so you can prepare. Right, so most probably, yeah, not most probably, actually, it's going to be the last 1 or 2 lectures, because I thought of doing some practical also with you. For the exam, you won't be getting any practicals, but you should be able to read the outputs. Sometimes I might give you an ANOVA table rather than asking you to construct it and do interpretations, do tests and all that based on that, right? So you should be able to read the output and identify, okay, this output means this. So quickly, I will do a little practical to end the lecture, and most probably that would be either next week or the other week, because I have to talk about categorical variables as well, how to incorporate dummies and all that, because so far we discussed all the quantitative stuff here, continuous scale variables, and there could be categorical variables as well. So how to incorporate multiple linear regression when there is a categorical variable, those things should be discussed. That is going to be a very small lecture. We'll see how it goes. If we could finish it off by around less than 1 hour, we can at a stretch do the practical and finish off. If not, the practical would be the week after, and that is going to be the end of the lecture series. You won't be getting any practicals for the exam, but you should be able to read and understand the output that we get. Okay, and I think it would be beneficial for you all to do some practical, because in practice you won't be computing these things manually. You anyway go and use a software. So to have that experience, I think it is important for your future research and all that. So let's do it in that way. Thank you very much for participating today's lecture. If you don't have any questions, you all can leave the meeting. Thank you very much. Stay safe.